Today I want to talk about linear model predictive control and how to implement it in MATLAB. So here you can see a summary slide where we see the result that we're going to get from this exercise and the system, the plant that we are using as an example. It's a very simple plant. It's an object, a mass pushed over a surface, sliding on this surface, subject to linear friction, and K is the linear friction coefficient. This is the architecture of the control system. So we have the set point going into the model predictive control algorithm, which includes, in MATLAB this is embedded, and it includes a Kalman filter. So this is important. We always need a state estimator for model predictive control, and we will see why later. Then this controller produces a control input, the force to be applied to the object to control the position in our example, which is read back into the controller. Now here you can see the address of the GitHub repository with the code related to this example. This is my website. You can find various examples on control systems on my website. There is also a course on PID control if you are interested. And also I have a LinkedIn account that you can check if you're interested in this kind of posts. I post a lot of stuff there, so I'm sure you will find it interesting. So let's see the theory behind model predictive control. Essentially, the idea is to find the optimal control sequence that minimizes a cost function over a certain prediction horizon. Okay, so the prediction horizon is a series of steps over which we will run the optimization. The cost function in this case has this is an example. Okay, the cost function can be anything. We can have a customized one. This is a relatively frequently used one, which is composed by 3 quadratic terms, and one term is accounting for how well we're controlling. So the difference between the set point and the control variable, and it's this term weighted with its own weight. Then we have an element that is there in case we want the control input to be preferred on a certain value. Okay, so if we have a target control input, this is the target in this example. We have another quadratic term that will push the control input towards that target. Okay, in case there is a target. Then there is another term that controls how aggressive generally the algorithm is, and it's the rate of change of the control input. Okay, how much the change for every step. Also, something that is not indicated here but is frequently exists, and it exists in the MATLAB ecosystem for creating MPC controllers, is the control horizon. Okay, so the idea is that the prediction horizon is how many steps we optimize on, and the control horizon is smaller than the prediction horizon, and it's how many times we can change the control action. So if we have control horizon 2, it means we can only change the control input for the first 2 steps, and then we have to keep it constant for the remaining of the prediction horizon. Okay, this is our plan. We have already discussed it's an object sliding on a surface, subject to our force, which is our control input, and also subject to linear friction with coefficient K. Z is the position of the object, and using the law of linear motion, we can we can write this equation, this differential equation. So the mass of the object multiplied by the acceleration, which is the second derivative of the position, it's equal to the force minus the linear friction coefficient multiplied by the speed, which is the first derivative of the position. Then the mass is 10 kilograms, K is 0.5 Newton per seconds divided by meters. Okay, these are arbitrary numbers just for this example. The state space model. Okay, we need to write the system in state space form for the model predictive control algorithm to function. So this is how we do it. The state space model, state space form should be relatively familiar. So we have to express the system with a state vector, in this case x, and we have to express it as the derivative of x with respect to time is equal to a matrix A multiplied by x plus b, which is another matrix or vector, multiplied by the u, that can be also vector, which is the input. In this case it's just a scalar input. And then y, which is the output of the system, is vector or matrix C multiplied by x plus vector or matrix D multiplied by u. So our u is the force, as we have already discussed, and our state vector is the derivative of the position, so the speed in this case of the object, and the position of the object, z. So with this definition we can see that these are the A, B, C, D matrices that describe the system as we have explained it before. The control architecture. We have more or less already said enough about this. Just I want to remark again that we have a Kalman filter embedded in MATLAB in this case, so it's the ecosystem provides the Kalman filter almost automatically, and the Kalman filter will estimate in this case the speed, because we have only the position. In our example we are only reading the position of the object and we still want to run the model predictive control. So we need something, in this case the Kalman filter, that estimates the vector x. So in this case z dot, the speed, and z, the position. Okay, for the code I want to go on MATLAB and show you the code and run it. Okay, so this is the repository, how you will see the repository if you go to the address that I showed you before, and this is the code. So parameters, we are just creating the parameters. I will run the section. Then state space model, again the matrices as we discussed earlier. And then we create an object, which is our system, our state space, our system in a state space form, and we use the ss command to create it. So again, run section. I'm using run section so that you see what I'm doing. You can run these sections also using control enter. Okay, the MPC object, we create three structures here: manipulated variable, output variable, and weights. And here for the manipulated variable we set the minimum and the maximum, so we are assuming that we can only use a force between minus 10 Newton and plus 10 Newton. And the scale factor. The scale factor is a normalization factor. Okay, so it tells us what is the range of the force in this case and what is the range of the output variable in this case. And it's used to put them on the same scale in a certain way. So you can imagine if your input has a range of 0 to 100%, for example, and your output has a range of 0 to 1, you might want to put them on the same scale so that they will have the same weight, they will count the same in the cost function. And this is how you do it, okay? So you put them on the same scale. So in this case, this means that if I have a force 10 and I have a output variable 2, they will have the same importance on the cost function, okay? Okay, then for the output variable, the limits are -2 and +2. It's not going to matter in this case because we're not getting there. The set point is 1, will be 1, so it doesn't matter. But in the future, we will see a lot of examples on constraints, so it will be important. Then the sample time is 0.1 seconds, and here we use the command MPC to create the MPC object. Okay, and we pass the object dynamics in state space, then sample time, prediction horizon, 10 steps, which means with a sample time of 0.1 seconds is 1 second in the future, 10 steps in the future. Then only 2 steps for the control horizon, so we can only change the control input for the first 2 steps, and then it has to be kept constant. So this is what the MPC will do at each iteration. Then we pass the 3 structures that we created before. And let's go with run section. Okay, here we simulate the controller. So we want to set the simulation time, it's 5 seconds. Then we calculate how many steps we have with our sample time. Then we set our reference signal set point to 1 for a number of elements, that is how many steps we have. And then we use the command sim to simulate the MPC object. We pass also the steps and the set point. And it will give us three outputs. The output, so the position in this case, the time, and the control input. So let's run this. Okay. And then we plot. Okay, now the plots are relatively simple. I have a lot of commands because I made them on black background and I wanted to make them nice colors. But really, all there is here is that we're creating the figure, then a subplot with 2 elements vertically, 2 plots vertically. Then we are using stairs instead of plot because it is all a discrete simulation in this case. Okay, it's all in MATLAB, so it's all discrete. There is no Simulink here that is changing the time step. It is simply the MPC using the discrete model of the continuous model that we've given to it. Okay, so it's using this state space discretized to simulate it internally and running every 0.1 seconds. So there is no, I prefer it to be plotted as steps rather than interpolate between the points, because it gives us an information that is not there, it doesn't exist. Okay, so stairs of the Y, so the output, then stairs of the set point, and this is the first plot. Then the second subplot is the control effort, so again stairs of T and U, and then there is a bit of stuff to make the lines bigger, a dashed line for the set point, and so on. Okay, no, not much more. Let's see what we get, which is more interesting. Okay, so this is this is the response. Let's see if I can move this. Okay. Now we see we get a fairly nice response. Obviously, it's very easy, okay? I want to make sure you get this. In this case, we have given a model to the MPC, and we are testing it on exactly the same model. So it's like we know perfectly the model of the plant that we are controlling, which is never the case. But this is as an example, okay? We start from here, then we will see how to go into the nuances and the complications. But this is what we get now. Very good response, a little overshoot. And I think what is very interesting for me generally with MPC is the control effort, because it's how the constraints are handled. They are essentially embedded in how the MPC algorithm works. So this is one of the most powerful features of the MPC, constraints. Okay, so here we see that it knows straight away that it can max out the forwards, so it goes to 10 straight away from the beginning, then it starts going down quite sharply. It's not super sharp because I've put a weight on the rate of change. If I didn't have that weight, it would probably go from 10 to -10 perhaps in just one sample time, okay? But that obviously you understand that it's more aggressive, and it might be less robust. It could be more prone to instability, which is why we put a way to balance performance and robustness. So it goes then to -10, stays to -10. It's basically breaking it, okay? It's breaking the box that is lighting the object. And then it goes more or less nicely to 0, which is where we need it in this ideal case. Okay, it's everything for today. Thank you for watching. I'll see you in the next video.